1 to infinity?
Ants.
What?
The pool is filled with ants.
Filled with ants?
Like a bunch of ants are in there. Like we're on Benjamin's floaties, all huddled up, and in the water, all huddled up, and still alive.
Oh yeah, ants do that. They'll all cling together
Mhm.
because they have surface tension. Greater than water, and that's how they survive on water.
Mm-hmm.
Until they float off into something that's
Yeah, there's no cousins.
Right.
and like the dead ants won't float, so by the time the bottom layer dies, like it's just like a solid platform.
Why don't you go pick the ants out of the pool?
Yeah,
So these are not intervals of convergence that are allowed. Like the domain of the power series is very boring. It has to be a symmetric interval about the origin.
okay.
Well, not the origin, but the center of the
Yeah.
series rather. So x naught. This is what you got.
Yeah.
These are not possible for
Yeah,
power
that's
series.
Yeah.
Right. Now these are domains for a more general series, like something called the Frobenius series. You can have something like this. But power series, kind of boring. I'm currently talking about real calculus. In the complex case, these equations are still legit. It's just you have to think about that as modulus in x. So like in the complex case, the domain for power series literally is either a point, a disk,
Yeah.
but it's complicated. Like the disk, it's much more interesting for a complex case. You could have something like this, where like this part of the disk is included, but these guys are not. All kinds of wild, wacky stuff is possible. So yeah, but there is either a disk of finite radius, or it's the whole complex plane. If it's the whole complex plane, then the power series, the function which is represented by the power series is said to be an entire function. Likewise, in the real case, if the interval of convergence is the whole real line, it's said to be an entire function. In calculus 2, you're supposed to be taught that you can use the ratio test to pick up the radius of convergence. The ratio test says that the limit, if you just study the limit, is equal to infinity of like a sub n plus 1 over a sub n.
Yeah.
If this is equal to L, which is less than 1, then I forget the best statement here. Anyway, this well, actually, fine.
Hey, you pick up the ants?
No,
Why not?
they're really big. For ants.
Makes sense.
Yes.
So you got to swim there.
No.
I believe that says that the radius of convergence is 1 over L, if I remember right.
But I don't know why they're so big. Like, I don't know why, but they're
I feel like
hiding in
forget.
the corners of Benjamin's floaty.
Anyway, let me not get into all that. The point is, there's a ratio test. You can use the ratio test
Why is the floor?
to determine the radius of convergence here. And it's very cut and dry, like it converges within the disk and it diverges outside. So that's the backdrop with which we
Yeah. The
come.
complex cases are
Can I
really
look
cool
at
like
how
this.
Bingo?
Yes. Oh yes. Very, very fun stuff.
Um,
So if you look at my section on series, it starts out pretty much the same. I define the series and it's converging if its sequence of partial sums converges. I develop a Cauchy criterion for series, typical stuff. The nth term test still works. Hooray! If the limit as n goes to infinity of a sub n is not equal to 0, series diverges. Good news. All right. Comparison test. Actually, still, we're in the clear. It's the normal result. If you have a smaller series which
All
diverges,
harmonized with
the larger series likewise diverges.
soap.
If you have a larger series which converges, the smaller series must also converge. All of those things being judged relative to the norm on the algebra.
Oh, they're over
Nothing too
here.
surprising there. Here's a kind of funky 2x2 matrix sequence example. Yeah. See that? 1
Yeah.
over n squared, 2 over n squared. So you know what each component sequence there, it's like pi squared over 6, right?
Yeah.
Or 2 pi squared over 6, 3 pi squared over 6. And, yeah. But the norm anyways ends up being square root of 30 over n squared, which of course converges to, well, that isn't, the series, square root of 30 over n squared converges to pi squared times 30 over 6. Let's see here. You talk about absolute convergence. The series converges absolutely if the norm of the series converges. Right.
Oh, I doubt, because I did Cal 2 like 2019, so that was when everything got shut down.
I hear you.
So I'm pretty sure you just forgot what he did. He was like, yeah, I think we had like a final, but he didn't cover anything on, because I don't know why they do series and last in Cal 2, but that's how they do it. And all my friends said that they did series first and then they did all the Cal 2 stuff. So like I was helping them with integration and they were like doing series because I had done the integration stuff before them. But yeah, we did series last. And
Interesting.
so yeah. And then yeah, like our final had nothing to do with it. He just gave us
I see.
some homework questions and he was like,
Well, so let's see here. In short, and then we got theorem 4.8 is the usual result. Absolute convergence implies convergence. That's what's usually the case. The converse direction is never true, even in the real case. Like you have series which converge, but the absolute value of the series does not. Those kinds of series are called conditionally convergent.
okay.
Famous theorem by Riemann. The Riemann rearrangement theorem says that you can take any conditionally convergent series and rearrange the terms to make them converge to whatever you want. So like changing the order in which things are added in a conditionally convergent series can change the value to which they converge. Many of the like minus 112 kind of things are based on manipulating something of that nature.
Yeah.
I think it's worse than that for that minus 112 thing. Anyway. I have a root test. So for the root test, you look at the lim sup of the nth root of the norm, and don't worry about the details at the moment. It gives you either convergence, divergence, or no information at all. This is still kind of pretty normal.
Yeah.
All right.
Complex series.
Yeah, there's an example. And then the ratio test.
Didn't we just do that?
Yeah, but now this is a calculus, so that was
Reals.
reals, yeah. So we get, and this ratio test gives you absolute convergence. So there's more. I could have told you more about power series. Not only do power series converge on some interval like this, they converge absolutely on the open interval of their convergence. So like ignore endpoints. Absolute convergence is very powerful because absolute convergence allows rearrangement. If an absolutely convergent series, you can shift the terms around and add them in any order you like. You don't face that weird thing I'm telling you about with the conditional convergence. So absolute convergence is very important for calculation.
You would think that would be the case for just some natural numbers, because it's always infinity.
Yeah,
Never converges.
conditionally convergent stuff is like it'll mess with your intuition. So, but again, here the ratio test for, and I should clarify, these results are for numerical series in the algebra, right? These are not power series results yet. So let's go on here. Theorem 4.13, the sum of two series is the sum of the series, and you can multiply numbers in the algebra. Essentially, straightforward application of the sequential theorems already proved.
That's my mother, sorry.
You're fine.
Hello.
I'll allow it.
Oh, no, I can't come. No, I can't. I gotta go to Livingston tomorrow. One of the people called me back for the apartments. I'll try to come Friday if I can, but I mean, it's not gonna be till late. Yeah, so you guys are gonna be gone. You guys will probably be gone. You guys will probably be gone by the time I get there. Okay. Okay, well, I'm gonna get back to doing my research. Alright. Yeah. Maybe tomorrow night. Okay, here. Call you later. I will call you later.
So if we look at theorem 4.15, so like adding two series term by term, multiplying a series by a number, term by term, pretty natural. You may not have thought about this much, but when we multiply two series, it's not necessarily the case that the natural product of two series is another convergent series. Because the process of multiplying two series, first of all, what do you mean by multiplying two series? Well,
Are you multiplying component-wise, like each nth term with each nth term, kind of like a dot product?
it's like distribution, so
Ooh.
yeah, exactly. So something like if I have a1 plus a2 plus times b1 plus b2 plus well then the product series is going to be a1 b1 plus a1 b2,
A2
plus
B1.
a2 b1 plus a2 b2 and so forth and so on. So
That's nasty.
you're like, well, but which order are you putting them in? That's right. Which order are you putting them in? So actually, the absolute convergence becomes important here. And so the standard thing is, I think it's called a Cauchy product, and it's theorem 4.15 defines it. See, I say you have A is the series A sub n is absolutely convergent. You have another series B that's convergent. Then you define Cn to be some n k equals 0 to n of a sub k star b sub n minus k. All right? And then the sum n equals 0 to infinity of c sub n is then going to actually be equal to the product of a times b, where a and b are what the series A series converges to, and b is what the b series converges to. So this is also what's known in the real and the complex case. Or I probably should say real case. If you have an absolutely convergent series times another convergent series, the product is defined. It suffices to have absolute convergence of just one of them, like no need for both.
Oh.
So that's kind of cool. But the proof is here, and it's, again, actually it's not that bad, but it does sort of heavy-handedly involve the submultiplicative constant and some somewhat delicate arguments, but they're there. I claim that if A is not commutative, A could give a similar argument if I was given the absolute convergence of the other series. So I don't know. I think when I was looking at this, we'd come to the conclusion that we could make this argument for non-commutative algebra just the same. So, all right. So that brings us to section 5, which is finally kind of to the part I think is more interesting: power series.
Yeah.
This is where it gets really weird. All right. So, first of all, power series is what it sounds like. It's a function whose formula is defined pointwise by a series. So you can find coefficients c sub n, and over A calculus, notice that there's a multiplication here. And that's a multiplication in the algebra, right? I mean, that's an algebra product. And the fact that that's an algebra product, it monkeys with everything. I think it really messes up the standard theorems. Because in the reals or the complexes, you have this simple identity. Take the norm of this,
Mm-hmm.
Oh, excuse me, well, you take the absolute value of that, Well, that is equal to the absolute value of Cn times the absolute value of z minus z naught, or the modulus of z minus z naught to the n power, because the absolute value function or the modulus of the complex numbers is multiplicative. There's no less than or equal to there, there's an equality there. But over an algebra, that does not happen, because you have,
The absolute value would only have the Cn.
well, let's see here. So you get like the norm of Cn, right? Because it's an algebra number. And forgive me, I forgot my submultiplicative constant. And then but then to break this down further, that's, so I get, this is less than or equal to m sub a squared. And it gets so forth and so on. I mean, that's m sub a to the what power?
Can you get a power series just trying to?
I think, and I'm trying to figure out how many of these I get. If I get it all the way down to, I have trouble counting, So if I get all the way down to there, how many m sub a's did I pull out? I mean, when I got this to n minus 1, I pulled out 2 of them. When I got this to 1, I got a 2. I think this ends up being n plus 1, if you think through it. Because okay, so let's do 3. And I'll just do z. That's m sub a, norm of z squared, right? Which is then less than or equal to m sub a. Norm of z, m sub a, norm of z. So I get m sub a squared, norm of z cubed. So actually, I get n minus 1, don't I? Yeah. But the thing is, I got another m sub a from the Cn out here. So actually, if I do this carefully, I should get n, because I get n minus 1 from busting this up. I get n minus 1 of these from busting this up, but I also get the original m sub a because I got c times that. So Anyway, my point to you is we don't get equality here, we've got this pesky inequality, and that really rains on our parade. So, Lemma 5.2, what it's saying is if your center is not the origin, then you could shift it back to the origin. So if we understand how series work at the origin, we can just translate our results everywhere else. So Lemma 5.2 is just about allowing us to choose well, I guess I don't really make good on it, but if I really believed in Lemma 5.2, I would just give arguments for z equal to 0 for the rest of the section rather than at z naught. But as you can see, I still start saying stuff about z naught because I think I want it to be directly readable, each theorem in it to be directly readable without like thinking about the totality of the section. Yeah. So look at this. This is the root test. You notice that the radius for convergence.
Oh, it has that multiplicative.
Yeah, has the A in it, right? So typically it's just 1 over alpha, where alpha is the lim sup of the nth root of the absolute value of the coefficient, and then goes through. So you get absolute convergence for less than that radius. If alpha is equal to 0, it's entire. But here's where it gets weird. There's nothing here about divergence. In the real case, if you have in the real case, if you're having the norm of z minus z naught greater than or equal to r, or greater than r, equal is always fussy. Equal is always this funny business, or endpoints. But greater than, game over, diverges. There's a disk of convergence. We lose that.
In algebras?
In algebras. Because the equation 47, it's not equality, it's inequality. And so
47?
yeah, 47 there.
Oh, okay. Hence, z modulus z is.
Now, that alone is not proof that bad things happen. It's just, that's where the door opens. And I will show you examples soon of this, okay? Now theorem 5.4, what does this say? I say, if I have a power series which converges inside some R disk centered at z naught, then the lim sup of the nth root of the norm of the coefficient has to be less than or equal to the length of 1 in the algebra divided by r. Fun fact. You notice that the previous result was that tables were turned. We calculated the lim sup and stated that gave you an r. This is saying that if the thing converges within r, then the lim sup has to be bounded, not equal to, but bounded by the length of the identity divided by r. For whatever that's worth. Now this example 5.5, it pretty much is the weirdness. So you've got, what is 1 plus j to the hyperbolic numbers? You know, it is a0 divided by 2. And so Cn is 1 plus j for all n. So the norm is square root 2. And you can apply the root test and you get the limit as n goes to infinity of 2 to the 1 over 2n, which is a limit you would have skipped in Calculus 2 because of COVID. But in a full semester of Calculus 2, you might see how to prove that limit is 1. That is the sort of thing you need to study in advance of the subject geometry. All the stuff you missed in Calc 2, it matters. to the subject vary, unfortunately.
That's not too bad.
Right, I mean, it's, you know more math, it's nothing that you can't go back and fix. But,
Yeah.
there's a lot there, actually. So, anyway, the root test tells us that the series converges on a disk of radius 1 over root 2. Right? Because m sub a is actually, we can make m sub a equal to root 2 for the hyperbolic numbers. Yet, check this out. If we look at a z equal to a times 1 minus j, what happens when you plug that into the series? Well, you're going to get, what happens when 1 minus j hits 1 plus j? Well, it's 0. So everything in that series vanishes except for the constant term where n equals to 0 is just z to the 0, which is 1. So you just get 1 plus j from that function without regard to what a is. So the whole scalar multiples, the plus and minus infinity of 1 minus j, are all points of convergence for that power series, despite the fact that its disk of convergence is just 1 over root 2. Well, excuse me, the disk of convergence given to us by the root test is 1 over root 2, but in fact, we see from direct calculation that it converges way, way beyond that disk. And in fact, Daniel showed that there's a whole band, actually. It's not just that line that's problematic. It's if you go above and below the line within distance square root of 2 times the norm of epsilon from y equals, where's this epsilon?
Looking at 23.
Oh yeah, so is the page 19 right above equation 51? These calculations, he shows that if you put w equal to a plus epsilon plus j times epsilon minus a, you got the one over equation 51?
Yeah, 50. F of a 1 minus j.
The next page, the top of the next page.
Oh.
So,
Consider the points near y equal to negative.
so what? So what he shows there is that the norm of 1 plus j times w to the n, where w has that form, is equal to the square root of 2 times 2 epsilon to the n power.
Yeah.
And then he appeals to the numerical, the root test from numerical series. And he gets the lim sup of the nth root is 2 epsilon, after that epsilon. And so that just needs to be less than 1. For that to be less than 1, we just need the epsilon value of epsilon less than a half. And,
What does sup stand for again?
it is the limit, it's, the lim sup involves all possible subsequences, and so it looks at the, what happens, it's a,
I was thinking of something in abstract anyway.
no, it's something you should study, possibly in real analysis. It's the limit supremum. It is a limiting concept which involves subsequences. I'll just say that, but let me draw a picture. So, what's going on here is we've got this series, right? 1 plus j, z to the n, right? N equals 0 to infinity, right? And the root test gives us that there's this disk of radius, 1/√2. But then we very early noticed that 1 minus scalar multiples of 1 minus j. So what's that? 1 minus j is like here, right? No, here, right? I guess it's out here. It's out here actually, yeah. Well, and then so anyway, this line, whole line, right? That's something to perform a times 1 minus j, right?
Mm-hmm.
So f of a minus is just equal to 1 plus j. Of course, that definitely is fine, right? I mean, series converges along that line. And then the w calculation that I was just sort of mumbling through is showing that, in fact, it's not just that line. You can, from applying the numerical series, you get this whole band. They're actually, all of these points is converging. Because the w, it's, as he explains, distance of the square root of 2 times epsilon, which is less than 1/√2. So I guess that makes epsilon less than 1/2, right? But then what was the w formula? W was equal to what? It was a plus epsilon plus j times epsilon minus a. Or in other words, it's a times 1 minus j, right? Plus epsilon times 1 plus j. So all I'm getting at, Audrey, is like this point he's looking at. So a times 1 minus j might get you to like here, or wherever. And then, so you're like somewhere on this line. And then you're adding epsilon times 1 plus j. What is that? 1 plus j. 1 plus j is the vector of 1, 1, right?
Yep.
So you're basically going like that. But this epsilon is what? It's at most
Oh, 1/2.
1/2.
So it stops at a point.
Mm-hmm. So how long, what's the length of this vector? The square root of 2, right?
Yeah.
So you're going like, this is going square root of 2 vector, half of the square root of 2 vector. So like this is at most 1/2 of the square root of 2, which is 1 over square root of 2.
Which, so at that point, that section right there is converging towards there.
I mean, it literally
Yeah.
is just the shadow, if you can imagine a line being here. Going,
Yeah.
I mean, it is literally just fitting
Yeah.
the tangent lines to.
Okay. The
Yeah.
disk.
So this really weirded us out when we first found it because it's nothing like that. I mean, it's just the root test doesn't really give us very good insight as to the extent of the convergence, Like it tells you some places where it's convergent, but it doesn't tell you the whole story for sure. And this is just something we have to deal with in algebras, is like the usual convergence tests only give us partial truth. Like there can be points of convergence outside where the convergence tests work. That's the weirdness. Let's see here. Geometric series, theorem 5.6.
Yep.
It's not bad. So the sum series z to the n converges to 1 over 1 minus z for as long as 1 minus z is a unit and the norm of z is less than 1 over m sub a.
Oh, okay, and you did this proof really similarly. Uh-huh. And get the multiplicative, yep.
Now, there's something to connect here, right? Um,
Hmm? I think we making forces.
Why?
We're making forces.
Oh, I haven't done it yet.
so as you know, there's an isomorphism from the H2 to R cross R,
Mm-hmm.
and
When you transport over series, what happens?
yes. So it's kind of like if you just go term by term, what happens there, and what would the natural transference of series be? How do we take a series in one algebra to a series in another algebra? How would we?
Well, I think you
Sense
do
of that.
component-wise, right? So you have two equations and R cross R, especially for H2 is kind of nice, I assume. And then when you transfer them over, it would give you something. I would definitely look at how the maps look. So if you took one series, like if you took the powers, like I don't know, if any given series, if you look at the mapping of it on H2 versus the mapping of it on R cross R, and see how those, and see what you can see just by looking at the pictures. I think that would be one way to analyze it, is looking at the geometry of it.
Yeah, I think you're right. I'm trying to think here. So this example 5.7 is on the direct product algebra.
Yeah.
So what is the geometric? So first of all, some multiplicative constant in the direct product algebra is 1. So like m sub a is 1. So the theorem 5.6, I say, provides convergence that the norm of z is less than 1. So if we use the usual norm on the direct product algebra, that's just the unit circle. However, if we calculate directly, as is shown in this example, z to the n is x to the n comma y to the n, and each of those component series is geometric. It's a real geometric series, so it converges minus 1 to 1. So
Converting minus 1 to 1.
yeah, x. So I can draw a picture here. So basically, the point of example 5.7 is that in the direct product algebra, these, z equals x comma y,
Yeah.
z to the n equals x to the n, y to the n. All right, so like this, we look at the series. These are both geometric series,
Yeah.
real geometric series, in fact, and so this is just a equals 1, r equals to x.
Yeah.
So this converges to 1 over 1 minus x,
Yep. And that
Yeah.
converts to y.
1 over 1 minus y, provided that f sub of x is less than 1 and f sub I of y is less than 1. So f sub I of I, where does this calculation make sense? F sub I of x less than 1, that's between those two lines. And if-
Oh, and it gives you a square.
right, yeah, it gives you squared. Where does the theorem 5.6 tell you that you converge? It just tells you you converge on the
the 1m multiplicative.
The disk of, you know,
Yeah.
it just gives you this.
Gives you a unit circle.
Yeah. So it's missing so much, right? I mean, well, so much, I don't know, but it's missing this part.
And you can see that, and but when you switch back over, you see that as well. Oh, we're talking about R plus R, not necessarily hyperbolic space.
Okay, so, right, but I do think it's relevant because, okay, so that, it's basically what I explained in the paper next, is that we thought about this for a while. And so here's the band of convergence for sum of 1 plus j z to the n, right? That's the band of convergence. We talked about this for a little bit.
Yeah.
By very similar arguments, the band of convergence for the sum of 1 minus j is this. So where can I add these two together? In here.
In the circle.
Well, in the diamond.
Yeah.
So in that diamond, they're both defined. And what happens when you add these two together? You get the j's canceled,
Yeah.
and you're left with 2z to the n. The 2 is essentially irrelevant. So this series
Exists.
converges on the diamond,
Yeah, but it's rotating 90.
right? But this is in H2, not, this was R cross. But my point is this,
Is that?
I think so,
Some,
in a sense.
I want to know why it's rotated though.
But the thing is, this here, if you study theorem of 5.6, the ratio, or whatever it was,
Yeah.
then you don't get the diamond, you just get
Yes.
Am I still able to?
that as the domain of convergence for this.
Yeah.
But it's actually that.
Youth is
And-
going on to sixth grade.
Let's see here, what was your isomorphism? The isomorphism
Fifth grade math
For-
sixth grade.
What? Which
You,
one?
you won't be there
for,
grade
let's see, I'm
one.
trying to remember, we got a few different ones, but if we go psi from, say, H2 to R cross R,
Yeah. This is the one you did. I did H3 and up.
I'm trying to remember, this one of x plus jy is, I want to say it's x plus y, x minus y.
Yeah.
Right. Because, yeah, psi of j is 1 minus 1. So, if I look at psi of x plus jy to the n power, I get x plus y to the n, x minus y to the n. So alright, so like, if instead of using x and y here, I use like, let me call this one x1, call this one x2. In other words, I get x1 equal x plus y, I get x2 equals x minus y, right?
Yeah. So,
So-
you can take that and convert, and do the convergence on.
Yeah, I want to show that this isomorphism actually maps that region to that region, I believe. And so we have that the absolute value of x1 is less than 1, right?
Mm-hmm.
If we're looking, and the absolute value of x2 is less than 1, right? But when you, that's what? That's absolute value of x plus y less than 1. Absolute value of x minus y less than 1. What's this? Well, this is minus 1 less than x plus y less than 1, minus 1 less than x minus y less than 1, aka minus x minus 1 less than y less than 1 minus x. Minus 1 minus x less than minus y less than minus x plus 1, right? But that's x plus 1 less than y, not less than, a multiplier, right? Greater than x minus 1, right?
Yes.
So I have this and that. So these inequalities I'll write it the other way. This is x minus 1 less than y less than x plus 1, right?
Yeah.
So I believe I would like for that to be y equals to x minus 1. I'd like for this one to be y equals to x plus
And any other things for the resolution?
1. And then we
Yeah,
just
this is minus x. Another 1 minus x.
I may not be,
Alright.
yeah,
Minus x plus 1.
I might not be exactly right. Like, I'm not sure.
Yeah, they're not going to the origin. They're not the origin.
Well, I'm just trying to think of what these are, these points here. Because this was, I think we said it was radius 1 over root 2.
Mm-hmm.
So if we've got
Well, those points should all be 1.
I mean, I want that to be the case, right? So this distance here is 1 over root 2, right?
Yeah.
Like this distance right here.
Oh, I see the problem now.
And
Because you get a bad triangle.
but maybe if I'd drawn this correctly, would this be?
The points are 1, and the radius is 1 over root 2. Can't you like draw a triangle? That right triangle is 1, 1, 1. Oh, but is there a the radius from the center of the red line is root 2? And
I think that's what it was. Well,
yeah, but your hypotenuse would be half. It wouldn't be 1, so it'd be.
Just worry about
10 minutes, okay. That's good. I don't think I got more than 10 minutes left in me. 1 over root 2. The 1 over root 2 is the circle.
No, yeah, but the circle touches a point on the square, specifically the center, the midpoint between.
Right. So this is tangent.
Yeah. No, something gets off because if you do that, well,
I mean, this is the right angle.
wait, it's 1 over root 2.
Yeah, that's 1 over root 2. I'm looking at example 5.8.
So you get that. So that's 1 over root 2. That's a half, right?
Yeah, I feel like this also has to be 1 over root 2, right?
No, I think it should be a half. So it's the midpoint between those 2 points. Because if you draw the second tangent line, That should be a midpoint.
This distance is a half?
There's tangent right here, there's tangent right here. That has to be a midpoint, so it should be a circle. It's on a tangent. That's the touching the midpoint too. That's where it should touch these lines. So I think it should be 1/2. And then
This has to be a half?
no, that's the radius. I'm talking about the circle only touches the square at the midpoint. Everywhere else it wouldn't touch it. Oh, no. Not necessarily. No, yeah, it has to. No, but it's not radius 1. It could. Where would it? I'm lost now.
Yeah.
My geometry side. The radius of the circle is 1/√2. We're just square root of 2/2. Oh, would it even touch?
What do you mean?
Does the circle touch the border?
Which border?
Like, you see where it makes a diamond? Does the circle touch the diamond at all?
Here, and here. 4 points.
Yeah, so that's what I was trying to say. That should be a midpoint, but that doesn't make sense to me now.
Yeah, those gotta be midpoints.
Yeah, but then that would be 1/2.
Because 1/2, what, you mean 1/2 what?
Because every point's labeled on an axis, right? And it's 1 off. Because the intercept of it is at
I think
+1 or -1.
the question is what's the distance between those parallel lines, and I think the distance is square root 2. Which makes sense because it's 2 times 1/√2, which is root 2. For what it's worth, but
Well, this one has they all cross at 1, at 1, 1 or -1, or 1, -1. Right? And so where did the X intersect? And then if you solve for X, I'm gonna look at that more.
yeah, I think if you read example 5.8, that's pretty much claiming that what we're working on actually works out. But anyways,
I'm gonna
more next time.